Hello friends, I hope you all are well. In the last video, we have started the design guidelines for the thick film microcircuits. In that video, we have seen about the major steps on how to design a thick film microcircuits and a small topic how the resistors are designed in those circuits. So in today's video, we will continue the same topic, and in today's lecture, we will study about how the conductors and the capacitors are designed in the thick film microcircuits. So without wasting our time, let's start our today's topic. So these thick film microcircuits are also assembled on a ceramic substrate. Now these substrates can be of any material like alumina, beryllium, or aluminum, aluminum nitride. Okay, so but these conductors and resistors are applied on these microcircuits by using the screen printing technique, and then their paste are fired on these microcircuits. Okay, so now let's see the various functions of these conductors, which are how where they are used. So the number one is solderable connections, the connections. Second one is capacitance electrodes. Third one is resistor terminations. Fourth one is wire bonding pads, and the fifth one is crossover connections. So these are the five major functions of the conductors in the microcircuits. Now let's see the different materials which are used for the designing of conductors. So the number one is gold, second one is platinum gold, third one is palladium silver, and number fourth is copper. Now let's see where these materials are used. First of all is gold, which is used for good conductivity, good conductivity, conductivity and wire bonding. Second one is the platinum gold, which is used for optimal solder leach resistance. Third was the palladium silver, which is used for the design of low cost solderable conductors. And the last was the copper, which is a very good material, and these copper is used for low cost general purpose thick film conductors. So these are the places where these materials are used. So now these conductors can be designed as narrow as 8 to 7 mils, but for higher yields they can be designed around of 10 to 20 mils. So these are the values in which the conductors are designed. So these are the materials uh, of which the thick film microconductors are designed. So now let's move some further. So the thick film microcircuits have the ability to provide the conductive crossovers for higher yield. Now how this crossover is made? So the crossover is made by the printing a conductor followed by an insulator or dielectric layer, and which is also followed by the second crossover connections. Also, these microcircuits have also ability to form the multi-layer multi-layer dielectric layers by using the screen printing, the screen printing technique, the screen printing techniques between the conductors and the, or we can say resistor pattern, and simultaneously forming the vias in the dielectrics to interconnect the layers, which is a distinct advantage of these thick film microcircuits. So these conductors are made from one layer to the next through the small wires in the dielectric layers. Now The question come here is what this wires means. So these wires are nothing but an electrical are nothing but the and electrical connections electrical connections between the copper layers copper layers. These are electrical connections between the copper layer. So in this manner, we can fabricate 6 or more layer conductors for the thick film microcircuit. So this is the topic for about how we can design the conductors in the thick film microcircuits. Now let's move on to the next topic, which is how to design the capacitors for the thick film microcircuit. So now let's see how these capacitors are designed in the thick film microcircuit. So for designing of capacitors in the microcircuits, they can be easily fabricated and they can be ranged from few picofarads to thousands of picofarad. So let's see how some of the types of capacitors are designed. The first one is a substrate capacitor. Substrate capacitor. So these capacitors are of low capacitance value, That is why they can be easily fabricated by using the substrate as a dielectric. So how they are formed? They are formed across the substrate from an electrode on one side to the another electrode or the ground plane or the other side. So and how their values can be calculated, how their capacitance value can be calculated. So here's the formula, a small formula, that is C equal to epsilon naught epsilon r a by t. So what is epsilon naught? Epsilon naught is the permeability permeability of free space or vacuum, whose value is 8.854 multiplied by 10 to the power minus 12 farad meter per meter. Epsilon r is the relative permeability. A is the electrode area and T is the thickness. So this is how we can calculate the capacitance of the substrate capacitors. So the substrate materials, we have many types of substrate materials which can be used as a dielectric for this type of capacitor. But the most common is the alumina. Alumina can be used as substrate dielectric these capacitors. So that is why these can be formed using this method. But for large capacitance value, the substrate take larger space on the conductive plate. So the large capacitance value capacitors are used in the matching networks and the compensation circuits for in high frequency hybrids. So they are used in these applications. So this was the substrate capacitors, how they are fabricated, how they are designed. So now let's move on to the second type. The second type is the interdigital circuit. So these type of capacitors are used for producing the high pass characteristics by using the microstrip lines. So these capacitors have, you can say, long conductors, or you can say the fingers, which are used to provide the coupling between the input and the output ports across the gaps. Also, these gaps between the fingers and the end of the fingers are typically the same. Moreover, the length and the width of these capacitors, the interdigital capacitors of the fingers, are also specified. Since the capacitors are mounted on a substrate, These conductors affect the performance of these capacitors, and there are also some other factors which affect the electrical characteristics of these capacitors. They are as follows: the height of the substrate, the dielectric constant, the thickness of the conductor, and the resistivity of the capacitors or the conductors. So this was the second type interdigital capacitors which are designed in the thick film microcircuits. So now let's move on to the last topic, that is parallel plate capacitor. So the last type of capacitor is the parallel plate capacitor. We all know what is a parallel plate capacitor. It is the arrangement of electrodes and insulating material, or you can say the dielectric. And we can also calculate the capacitance of this using this formula, where in this thick film microcircuits, the thickness ranges from 12 micrometer to 60 micrometer. So this was a small topic of parallel plate capacitor, and there is nothing more to it. So now what are the characteristics of these capacitors? First one is the quality factor at 1 megahertz, which is 1000 to 2000. Second one is dissipation factor of 0.05% to 0.25%. Third one is insulation resistance at 100 volt DC is greater than 10 raised to power 12 ohms. Fourth one is breakdown voltage, which is greater than 400 volt AC, which is RMS value. Last one is temperature coefficient at minus 55 degrees Celsius to 125 degrees Celsius is less than 200 ppm per degree Celsius. So this was the parallel plate capacitors and the characteristic of capacitors. So with this we have completed the design guidelines for the thick film microcircuits. So I hope you understood our today's video, and see you in the next video. Till then, thank you very much.